Let's see now an allocation problem. In this problem, a supermarket is open 24 hours. We divided the day into 6 periods of 4 hours each. Each period needs a minimum number of cashiers. Each cashier works a shift of 8 consecutive hours, meaning 2 consecutive periods. Our goal is to decide how many cashiers to start in each period to cover demand at minimum costs. As we can see here, we need to cover the minimum required cashiers per period at minimum cost. First, we define the set T, 1, 2, 3, 4, 5, 6 periods, which represents the 6 4-hour periods. T gives the minimum number of cashiers required in each period. For example, in period 1 requires 7 cashiers, in period 2 requires 20, in period 3 requires 14, and so on. Next, we define the cost per shift starting in each period. A shift costs 4 hours per rate in start period, plus 4 hours per rate in the next period. In daytime, the rate is 20 per hour, so a 4-hour block costs 80. In nighttime, periods 1, 5, and 6, the rate is 30 euro per hour, so a 4-hour block costs 120. This block assigns the cost to each period, depending on whether it's night or day. We have 3 variables: xt, how many cashiers start a shift in period t; yt, how many cashiers are working in period t; and zeta, the total cost. We declare them as integer variables because we can't hire half a cashier. Here we define 2 equations, the objective, that is the cost function to minimize, and numero t, the coverage rule that links shift to actual worker presence. Here we define the lower minimum bound. This line enforces that the number of working cashiers in each period is at least the minimum required, nt. It's written as a lower bound directly on the variable yt. The objective function says that the total cost zeta equals the sum of all shifts multiplied by their costs. If we start xt shift in period t, we pay cost at time t, at period t, multiplied by xt, and the solver will minimize this equation. This equation instead defines how many cashiers are working in period t. It's those who start in this period xt plus those who start in the previous period xt+1, and for period 1 it also includes those who started in period 6, because the day is circular. So every cashier works for 2 consecutive periods, and we capture that with this formula. We put the whole equation together in model x2 and solve it as a MIP, mixed integer programming, because of the integer variables. The solver minimizes the cost zeta, and as output we display xl, that represent how many cashier starts in each period, y.l, that represent how many cashier are working in each period, x tot, that represent instead the total number of districts cashiers are in 24 hours, and zeta.l, that represent the minimum total cost.